All right, so this is 8.1, distribution of a sample mean. So the sampling distribution of a statistic is a probability distribution for all possible values of the statistic computed from a sample size n. The sampling distribution sample mean, X bar, is the probability distribution of all possible values of the random variable X bar computed from a sample size n from a population with mean mu and standard deviation sigma. A lot of this stuff is going to make more sense once we put numbers on it, but had to give you background information first. All right. So suppose that a simple random sample size n is drawn from a population with mean mu and standard deviation sigma. The sampling distribution of X bar has the mean. You have mu sub X bar is equal to your mean, your mu, and then your standard deviation of your sampling distribution will be the standard deviation over the square root of n. So like I said, right now we have symbols and words, but once you put numbers to it, you can see the process better. We are establishing the foundation. All right, the standard deviation of the sampling distribution of X bar is called the standard error of the mean. All right, then the last statement on this page, if a random variable X is normally distributed, the sampling distribution of the sample mean X bar is normally distributed as well. So you see what I have there in red? That means we can use z-scores. So that's why that's important. We can use the z-scores. All right, and I'm still copying this page before I go to the next. All right, so let's look at an example. It says the IQ of X of humans, IQ X of humans, in other words, the variable X is going to represent the IQ. The IQ of humans is approximately normally distributed with mean 100 and standard deviation 15. Compute the probability that a simple random sample size n equal to 10, in other words, sample size is 10, results in a sample mean greater than 110. So, oh, it's not gonna let me write. So you see over here, let me see if it'll let me write this way. It won't let me write on the screen. Okay, so we see our mean is 100, and I'll do it like this first, and I'll go back to it. So we have right here is our given information. Mean is 100, standard deviation is 15. Cancel that out. Sample size is 10. And then X bar is 110. That's the value that we actually have in question. It asks us about being greater than 110. All right, then our mean of our sampling distribution is going to be 100. If our original mean was 100, then according to what we just stated, that our mean also will be 100. So that's what we have right here. Then the standard deviation of our sampling distribution is going to be sigma over the square root of n. So that's why we have 15 over the square root of 10, which is 4.743. So those are the first things you want to establish from the given information. Is recognizing that your mean of your sampling distribution is going to be 100, which is the same thing as the mean of the population. Then the standard deviation of your sampling distribution is going to be 15 over the square root of 10, which is the population standard deviation over the square root of the sample size. And we got 4.743. All right, questions on what we've done so far? All right, next move to make is to find the z-score. So let's see what we did there. X bar minus mu sub X bar over standard deviation sub X bar. So that's your sample. All right. So it's your sample and distribution, sample mean, and the mean of your sample and distribution minus the standard deviation of your sample and distribution. So 110 minus 100 over 4.743 is equal to 2.11. Go to the z-score chart. So remember, we've been doing that the last couple of classes, going to the z-score chart. 2.1 on the left column, 0.01 on the top row, and that should meet at 0.9826. But don't forget, the chart always gives you less than. The chart always gives you less than. If you want greater than, remember that's what it asks for, greater than 110. So if you want greater than, you subtract 1, subtract 0.9826 from 1, and we get 0.0174. So the conclusion we can get from that, the probability of obtaining a sample mean IQ greater than 110 from a population whose mean is 100 is 0.0174. So it just depends on how my math lab, ask you or give you options for your answer. They may give you a statement, or they just may want the 0.0174. So at this point, you guys have seen the different ways that my math lab can ask you or give you options for your answer. All right, questions on what we did so far? All right, anybody still copying this page? All right.
No, I'm sorry. I'm not done, please.
Oh, okay. All right. Mm-hmm.
Okay, thank you. I'm done.
Yeah, not a problem. Not a problem at all. All right. Next one, the central limit theorem. It says regardless of the shape of the underlying population, the sampling distribution of X bar becomes approximately normal as the sample size N increases. And remember, approximately normal means a lot to us because that means we can use our z-scores. Whenever we see approximately normal or normal distribution, that means we can use our z-scores and our z-score chart. So if the distribution of the population is unknown or not normal, then the distribution of the sample mean is approximately normal, provided that the sample size is greater than or equal to 30. So we're looking for our sample size to be greater than or equal to 30, and that will be or produce an approximately normal distribution for us. But that would be the assumption anyway. Mm-hmm. All right, I scroll up some more. All right, so this next example, the mean weight gain during pregnancy is 30 pounds with a standard deviation of 12.9 pounds. Weight gain during pregnancy is skewed right. So it's saying that normally weight gain during pregnancy is skewed right. An obstetrician obtains a random sample of 35 low-income patients and determines their mean weight gain during pregnancy was 36.2 pounds. Does this result suggest anything unusual? All right. Make sure everybody copy. That's it for this page. I got to go to the next page to actually get to the work. So make sure everybody's done copying. So once again, the mean weight gain during pregnancy is 30 pounds with a standard deviation of 12.9 pounds. Weight gain during pregnancy is skewed right. An obstetrician obtains a random sample of 35 low-income patients and determines their mean weight gain during pregnancy was 36.2 pounds. Does this result suggest anything unusual? All right, can I go to the next page? All right. So we'll start with the given information. Our mean is 30. Standard deviation is 12.9. Sample size is 35. And the value in question, X bar, is going to be 36.2. Wanting us to determine the mean weight gain during 36.2 pounds and was it unusual? So that's what we're dealing with. So our mean of our sampling distribution is the 30 because that's the mean of the population. Standard deviation of our sampling distribution is going to be the standard deviation of the population or the population standard deviation over the square root of the sample size. So 12.9 over the square root of 3.35. It gives me 2.180498. And I just went that far in my decimals. The further you go out in your decimal places, the more accurate your answer will be. You don't necessarily have to go out 6 spots. I'll say probably go at least 4 though, at least 4. Once you've established both of those, you can go to your z-scores. Calculate your z-score, 36.2 minus 30 over the 2.180498. That gives me 2.84. Don't forget with your z-scores, you always round those though to 2 decimal places. Then we go to the chart, look for the z-score at 2.84, see what area is under curve, or to the left of that, that'll be 0.9977. And once again, that always represents less than or to the left of. All right. So since we want to know how unusual this is, then we want to know the chance of it being greater than, someone that we is dealing with this being greater than what we have. So we look up greater than by subtracting 0.9977 from 1. It gives us 0.0023. All right, and this is unusual because the probability is less than 5%, 0.05. All right, questions? Any questions? All right, so everybody okay before we go to the next thing? All right, so everybody okay? And I believe that's the last sheet for 8.1. Yep. All right, so that's it for 8.1. So let's see. So what I want you guys to do is for next class to try the process. See if you can mimic the process with number 19 on page 376. All right. So just try page 376 out of 8.1, number 19. They have A, B, C, A through F applying to the same problem. And so they just give you different scenarios, just trying to mimic the process. So I want you guys to try that out, see if you can get those answers, and then see if you have any questions before we go into 8.2. All right. Any questions? Any questions on? This is, just be honest, not an assignment, but it's something you should try before we go into 8.2. So, should I make an assignment? That would make people try to do it. So, yeah, I guess we can do that. Make that assignment for. I'll put it in my math lab. So, we have 3 in there already. 1, 2, 3, and 4. The last one came out of 7.2. So this will be assignment 4. Just one problem, but I want you to try or mimic the process that we just walked through in 8.1. All right. Questions, questions, questions. Like I said, it's A through F. And so just give you different numbers to play with in order to just, try to process over and over and over again. As a matter of fact, I think A, though, is just a regular z-score went from like 7.2 and then making you compare it. But you'll see it when you see. You'll see the directions. And if you have questions on anything, always feel free to ask. But either ask it next class or shoot me an email. All right. Anything, anybody before we close? Any questions on anything previous? Anybody have any questions on anything? Everybody good? Everybody straight? Okay. Try this stuff out. See if you have any questions. And I will see you guys on Monday. Have a great weekend. Let's see something in the chat. Oh, thank you. Thank you. Have a good